All right. Hello, everyone. Welcome to the August meetup of Women in Compilers and Tools. It is my pleasure to welcome Petra Hozzova as our guest speaker today. Petra is a PhD student at theorem, Austria, and a research intern at Microsoft Research currently. And she also previously did an internship at the smart contract verification company Satora. And before she started her PhD, she worked as a software engineer at Google. In her research, she focuses on automated reasoning with specific goals of extending it with the induction and using it for program synthesis. Today, she is going to give a very interesting talk on using automated reasoning to learn all about verification techniques. So the stage is all yours, Petra.
Thank you, Juby. So yes, exactly as Juby said, I'm going to give you an introduction to what formal verification is and how it uses automated reasoning. And please, if there is anything unclear during the talk, ask right away so that we can clear up any confusions before I continue on anything more. And yeah, if you post questions in the chat, then maybe also speak up because I might not notice them in the chat. Okay, so just to reiterate a bit of about myself that Juby also mentioned, and I put the slide here so that you have a bit of an insight into my background and see where I'm coming from when I'm talking about all these things like verification, software bugs, and so on. So exactly as Juby mentioned, I have a background as a software engineer. I worked as a software engineer for a little over 2 years, and after this experience, I went back to academia to get a PhD. I'm currently a fourth year PhD student, so about to finish in the next couple of months, hopefully. And I'm working in the area of automated reasoning, more specifically on a theorem prover called Vampire. And I will get around to what that is also later in the talk. And during my PhD, I had a great opportunity to work as a research and research engineering intern at two different companies. One of them was Certora, which is a smart contract verification company. So this was very practical and industry-oriented internship using all these techniques of formal verification and automated reasoning. And right now I'm doing an internship at Microsoft Research where I'm working on the internals of an automated reasoner or an automated solver Z3. Okay, so the main motivation of what all of this is about, this talk, and where I'm coming from, is that bugs can be dangerous and costly. And I guess we all know that, yeah, I see something in the chat. Okay, yeah. So bugs can be dangerous and costly. I think we're all familiar with this moment when we run some code, it doesn't work, and it surprises us because we're convinced that this thing should have worked. And this can lead to some serious losses. So as an example, so this is a Medium article about a rocket that had to self-destruct in the 1996. Thankfully, it was an unmanned rocket, but still the losses were pretty high. The costs were somewhere between $300 to $400 million just for launch of this rocket, and then billions of dollars in development. And the issue here was actually a very simple bug. They reused some software from earlier versions of the rocket, and that led to an overflow because the earlier software was using different format for some variables, so different types, and then when the software tried to store a value that was too large for a variable to fit it in, the rocket got off course and subsequently had to self-destruct just 37 seconds after initiating the launch. Then there's a different flavor of bugs that can be very costly, and those are the bugs in the crypto world. And this is again just a one of many examples where a hack led to substantial financial losses. This one's actually kind of interesting because the bug wasn't probably discovered by the attackers by themselves, but the error that led to the discovery of the bug was actually the fix that was posted on GitHub before it was deployed. And then the attacker was able to exploit it before the fix was actually deployed, leading to stealing over $300 million. And then finally, there is a yet different flavor of bugs, which doesn't directly lead to such huge financial losses, but can corrode trust immensely. And there was this glitch that American Airlines experienced in 2017 in their scheduling software, which allowed way too many pilots at the same time to take vacation during Christmas holidays. And there was a huge scare that American Airlines will have to cancel over 15,000 flights. And I think in the end, it was resolved by the airlines offering larger bonuses for pilots to actually take on the flights and cancel their vacations. So, of course, the question is, or I think we can all agree on the bugs really being something that we want to avoid, but the question is, how can we avoid these bugs? And the standard or the classic answer to this question is that we can employ testing. My claim here is that testing is a great technique because it can find bugs with the addendum that it can find bugs sometimes. What I mean by this is that even if you tell me that, oh, I have great tests because these tests ran and we verified that all of them passed successfully, there are no bugs. Well, I will tell you, okay, maybe there just is some bug that these tests haven't covered. So essentially what we know that if a test finds a bug, then yes, there was a bug. But if a test doesn't find a bug, it can be the case that the test just didn't cover all the possible bugs. And therefore, I advocate for an approach or method that is in a way complementary to testing, and that is formal verification. So the great idea behind formal verification is that this is a technique that can prove that there are no bugs, but again, with the addendum sometimes. But in a way, what I'm saying here is that we should employ both of these approaches to avoid bugs. So for testing, we can usually, in a fairly cheap way, verify there are no bugs of some sort, and we can find some if there are. And with formal verification, we can then, again, sometime verify that there really are no bugs. Okay, so what I'm talking about when I'm talking about formal verification. In this talk, I'll be focusing on so-called deductive formal verification, which is an approach that focuses on looking for mathematics-based proofs that some property always holds for a program, or that the program will never reach a bad state. And this is something that we can really rely on. So if we are able to find this mathematics-based proof, then the proof guarantees that the property really always holds. So if the proof tells us that this function call is always safe, after calling this function, let's say the balance on our account will always be a positive number or something like this, then we can really be sure that it is that way. Now, this sounds great, but I did have that keyword sometimes on the previous slide. So of course, the question arises whether this verification has some limits, or can we find a holy grail verification? Can we find something that would be a universal verifier? Can such a thing even exist? So let's see what that would mean if a universal verifier would exist. What I mean by this. So I mean some procedure or some program, some black box, or actually on the slide, a blue box, that would take as an input some program and a property, and it will tell us either that yes, the property holds for the program, or no, the property doesn't hold for the program. Now, let's assume that such a verifier would indeed exist. Let's see what we can do with that. We can build a new program, let's call it P, that would call this universal verifier as a subroutine. It will take the same inputs, some program and some property, call the universal verifier, and then invert its output. So if the verifier says yes, that property holds for the program, then our program P will output no. And if the verifier says no, then the program P would output yes. And you might be already seeing where I'm going with this. So what we'll do is we will call this program P on itself as its input. And we'll say that there is a property that we want to check. And the property will be that this program returns yes or returns no. So let's say the unifier tells us that yes, program P on input P with property, this program is returning yes, says yes. Well, then program P inverts its output and says no. On the other hand, if the verifier said no, then the program P will be saying yes. So we have a contradiction. And this is actually a very simple way of seeing why such a thing as a universal verifier simply cannot exist. Because if it would lead to a paradox. Okay, but not all is lost. Even though we cannot have a universal verifier, we can still have verification in practice. And in practice, it works like this. on the input, we have indeed the program and property, as we've seen before. But on the output, we allow a third option. And that option is that the practical verifier that we have can tell us unknown. It can tell us that, oh, sorry, I actually don't know whether the property holds for the program or not. And this solves our problem with the paradox. And this is how it actually works in practice. Okay, so the verification toolchain of a practical verifier consists of 2 steps. The first step is taking the program and the property that we have on the input and translating it into a logical formula. And already this is the step where our verifier can fail and say that this is unknown. I don't know how to translate this program and this property into a logical formula. However, if this step passes successfully, then we have the second step in our toolchain, and that is proving that the formula holds. And this is where automated reasoning comes in, the flavor of automated reasoning that I will be talking about later in the talk. These reasoners or solvers take the logical formula that we created in our first step, and they will try to prove the formula or find a counterexample to that formula. So essentially what we're doing is we're translating the natural language sentence, this property always holds for this program, into the formal language of mathematical logic. And we're passing this formula then to the prover. And if the prover is able to find a proof, then it means that the property really holds in all cases for the program. On the other hand, sometimes the prover might be able to find a counterexample, and then that counterexample will actually form the failing test case. It will tell us that for this specific case, the property doesn't hold, and from that we can derive the failing test. It can also be the case that the verifier or the solver that we're using to prove the formula tells us that this property doesn't hold, but I'm not giving you a counterexample. So in that case, we are not able to produce that failing test case. And of course, it can be, there's the possibility that the solver will either give up or run out of time or resources before it manages to prove or disprove the formula. And in that case, again, the answer is unknown. So let's see what sort of formulas and what sort of properties are we able to prove with in this way. So this is a toy example, a very simplified smart contract with one function that is depositing some amount. So all the variables that we're working with are, as it's usual for Ethereum blockchain, unsigned integers limited to 2 to the power of 256. We have a function deposit that takes some amount. It checks what is the current balance on the account. It adds the amount to the current balance, and then it returns the new balance. And what we would like to verify for this code is that if we're given any value, D, to deposit, then the balance before the deposit is less than or equal to the balance after the deposit was made. And we would like to check if this really holds for any D. Now, a short aside, since the value of D is actually limited, it is between the bounds of 0 to 2 to the power of 256. This could technically be also covered with testing. So we could technically write tests that would cover all the possible inputs. But this is in practice, of course, not feasible because they would have to go through all the possible values of D and also all the possible values of old balance. So such tests would take too long to finish. So instead, we'll be using formal verification. So what are we going to do with this? So going back to our verification toolchain, we have to take these 2 steps. The first step is translating the program and the property into a logical formula. And to do that, we have to first choose what logic are we translating it into, and then apply some algorithm for translation. So there are many options of what logic we can choose to use. And usually this choice is based on how the program and the property looks like. So for example, whether the program is using concurrency or not, whether the program or the property is using some complicated mathematical functions, or whether it is using some data structures and so on. For our example, we'll be using first order logic extended with the theory of integers, and I will introduce what I mean by these terms on the next slide, and we'll be doing the translation manually. So I'll just show you how to. form the formula based on how the property in the program looks like. But there are also tools that are doing this completely automatically. Then in the second step, we will be proving that this formula that we obtained really holds. And again, when we want to prove the formula, we have many options how to do it. Even for one specific logic, usually there are multiple verifiers or provers or solvers. They can be broadly divided into two categories. So they can be either interactive or fully automated. You might have already heard about the interactive theorem provers, or also called proof assistants. Those are tools like Isabelle or Agda or Lean. And these work very tightly in an interaction with the user. So the user poses the problem and then tells the prover that I want to take this sort of a tactic and try to apply to this problem. And the prover will then reply with, yes, okay, so you managed to reduce the problem to these subproblems. How do you want to continue with this? And then the user again chooses some other tactic, some other direction in which to push the proof. And the interactive prover is helping with making all the small and sometimes annoying steps because it can do those under the hood. On the other hand, the fully automated provers don't require pretty much any interaction from the user except for the user inputting the input file with the formula and setting some parameters. And then they go on and search for the proof completely automatically, completely by themselves. Now, the advantage here is clear that the user doesn't have to do actually much. The disadvantage here is that the user doesn't have that much control about or around how the solver searches for the proof, and therefore cannot guide the solver easily. And thus the solver might just fail. There is the possibility. Yeah, sorry. Is there a question? Okay. Well, there's a possibility, maybe there was just an echo from my slide, I don't know. There's a possibility of combining these two. So some interactive theorem provers actually call automated provers under the hood. So the user of an interactive theorem prover can say, oh, maybe I have some formula that looks like it can be proved completely automatically. Let's just try some fully automated solver on this. And then the interactive prover passes the formula to one or several automated provers, and if they manage to find a proof or disprove the formula, then they return this information back to the interactive solver, and the search continues in this way. And in this talk, I will consider, or we'll consider, two automated methods, and I will talk a bit about them in just a moment. But let's first take a look at the language that we'll be using. Yeah.
Hi. Yeah. So in your earlier slide where you showed the example, right? There was a function call. Get current account value.
Yeah.
So there could be any number of problems with that function, like as in values returned by the function or some reason for that to crash. So when you create this verification system, do you recursively go through the function calls that are made, or to prove if those have any problems, or is it just, do you assume that that function is going to be fine?
Yeah, this is a very good question. So it depends on what exactly are we trying to prove here. So here I actually have this hidden assumption that I'm assuming that this function won't crash. But I don't really care what is the value that it returns. The only assumption that I'm making is that it returns the same value here as it returns here. But otherwise, it doesn't matter what value it is. So I'm saying that for any current balance that is returned by the function, this property should hold. And but yes, in general, it depends on the system that we're using for the translation into the logic formula. So sometimes we might want to recursively verify also all the functions that were called, but sometimes it is good enough for us to rely on some assumptions like this, saying that, okay, we believe that this function won't fail when it's called.
Okay, thanks.
Sure. Okay, so coming back to the first order logic, which is the logic that we'll be using for encoding this formula. It is the logic, you might remember it from some discrete maths course. It is the logic that allows us to use variables. it has some constants, such as the interpreted constants of 0 to the power of 256, any other integer that might come to your mind, or also uninterpreted constants such as d, and that will represent the amount that we're depositing in our problem. It contains the symbols for functions such as addition on integers or modulo, or then uninterpreted functions, which we have to axiomatize somehow in our problem, such as the function deposit, which we are using to model the software function deposits from our smart contract. Then it contains some predicates, such as equality or less than equal. And then also it allows us to use logical symbols to put all these together into formulas, such as the conjunction, implication, and then quantifiers for quantifying over variables. So first order logic is the logic that allows us to quantify over variables, not over a set of variables. Now, the symbols that are highlighted here in red are those that are belonging to the theory of integers. Now, by theory, I just mean that these symbols have some specific interpretation. And when we say 0, we really mean the integer 0. When we say plus, it is always the same plus on, or the same addition on integers. And essentially, the theory that we are using in encoding our property in our program has then this influences what solvers or provers we can use, because different solvers and different provers support different theories. But the theory of integers is one of the more common ones, so we have a lot of options there. Okay, so using this language, we can translate our example into the following formula. So here, the first part is just saying that for any a, if we deposit a, then the result will be the same as summing balance plus a, and then applying modulo 2 to the power of 256. So this is just a translation of what the function does. The function first checked what is the balance, then added a to this value, stored it in a unsigned int with the upper bound of 2 to the power of 256. So that is where this modulo comes in, and then return this value, which is what is the result of deposit A. Then we have two more things here on the left-hand side of the implication. And those are requirements that the value of balance and the value of D are both within 0 to 2 to the power of 256. And this is, again, something that is coming from the fact that we are using uint 256. Then the formula continues with an implication. So what we had on the left-hand side of implication are our assumptions. So this is saying that if the program that we have really is this, so really has these requirements, then we want to prove that the balance is less than equal to the new balance. So the new balance is what we get after calling deposit D. Now, what we'll be doing is proving that this formula in fact holds. And if it holds, then it means that really when we have a deposit function defined as we have, and when we have these two variables, balance and D, then balance is less than equal to deposit D. So no matter what D are we depositing, what value D we're depositing, we'll get a new balance that is greater or equal to the old balance. Now, a technical step, instead of directly proving this formula, we'll be actually using proof by contradiction. So what we'll be doing is checking that the negation of this formula is unsatisfiable, or we'll be trying to derive contradiction from the negation of the formula. So the negation of the formula, that is, we get that by taking all the assumptions and the negation of the conjecture. So the conjecture here is that balance is less than equal to deposit D. So we just take a conjunction of all the assumptions and then also add to this conjunction the negation of balance is less than equal to deposit of D. And we'll be passing on this formula to our solvers or provers. To actually pass it to our solvers or provers, we have to encode it though in a language that the solver or prover can read. And for that, we'll be using the smtlib language. So this is the encoding of the formula. One note to start with, this encoding is using the prefix format for all predicates and functions. So for example, when you see here this assert greater equal balance 0, this means that we are asserting that balance is greater or equal to 0. So the encoding of our formula or example starts with a comment for the prover that is telling it what fragment of logic we're working with. Then there are some constant declarations So we're declaring the constant of balance, we're declaring the constant of D, and we're also declaring that 2 pow 256 is a constant. This is just, again, a technical thing. I don't want to copy this value that is exactly to the power of 256 too many times in the file. Instead, I will be using the name 2 pow 256. Then there is these two lines which encode what the deposit function does. So it tells us that for any integer amount that it gets, it sums up balance and amount and then applies modulo to pow 256. Then these 4 lines are the other 2 assumptions that we have, and those are restricting the values of balance and D to be between 0 and 2 to the power of 256. And finally, we have this assertion that is the negation of the thing that we're trying to prove, which is saying that the old balance is less than equal than the new balance, or the result after depositing D. And then finally, we have 2 more lines that are telling the solver first to check whether this formula is satisfiable or unsatisfiable, hence to check whether there can be a contradiction derived from it or not. And then in case that it is satisfiable, hence there is some issue with it, to also get a model. And this model will be corresponding to the counterexample to the property and hence to that failing test case. Good. So this is something that we'll be passing to our provers. Now, the question is how the provers or solvers work. And we'll be using... yeah.
So in your original program, you had these values as unsigned int, right? And
Yes.
Here you have it as int.
Yes.
Is that intentional?
Yeah, because we have to model it somehow within the logic. So one way would be to extend the language of the logic in some way to allow the type of unsigned int. But this might be problematic because then we would have to find a solver that natively supports such a thing. So instead, what we're doing here is saying that we're working with integers, because that is something that the solvers know how to deal with. And we're adding these assertions that are making the values into unsigned ints. So we're claiming that balance is must be greater or equal to 0. And we are essentially trying to prove our property, assuming that balance is indeed greater or equal to 0. So this is the way that we're modeling unsigned ints in logic.
Okay, got it.
Okay.
Quick question, Petra. Yeah. So the negation part, right? Like, can you tell a little bit about like why solvers, whenever we have to make any assertions or construct any logics, we end up negating all the time? Like, why do we do that in most of the cases?
So
like
okay, I think that the reason here is just the way that the architecture of the solver works. So the solver that we'll be using here, it is something called SMT solver, and I will explain in detail what it is in a minute. But essentially, this solver or this kind of solvers is made for satisfiability checking. So it can check whether a formula is satisfiable or whether it is unsatisfiable. But it doesn't produce a proof. So when we want to check that the formula is valid, hence it has to hold in all cases, we can do it by negating the formula and checking if it is unsatisfiable. But essentially, this is just one additional step. It's not really weakening the formula. It's not really weakening the problem. It's converting it in a problem that has the same expressive power. It's just the negation of the original problem.
Yeah. That part is clear. Yeah, thank you.
Okay.
Is it fair to say that to prove that, to prove the actual condition, you'll have to check it for every single value, versus for when you do the negation, even if it finds exactly one negation to be true, it means that it's it's done its job. It doesn't have to go on. So in that case,
I mean, if it finds that there is at least one case where the negation is true, it means that it found a counterexample to the original one, right? So that is like a yeah.
So just one example would be enough. Versus if it were trying to solve for the actual condition, then it would have to, find basically test everything out.
Yes, exactly. Yeah. So this is the way that we can use these tools that are essentially good at finding this one counterexample, but also they're because is, in a way, it is harder to verify that this really holds for everything. But at the same time, this is exactly what we're doing with checking whether the negation doesn't hold for some value. So in a way, it's it's an equivalent problem, but it's yeah. Okay, any more questions at this point? If not, then let's continue with automated reasoning. For those of you who haven't heard of automated reasoning so far at all, the easiest way to get an idea of what it is doing is to think about how you're thinking about mathematical problems, or how humans are thinking about mathematical problems in general, and then just make it many, many times faster because it happens in a computer. So essentially, the formal automated reasoning that computers do is similar in a way to what humans do. We take what we know, and then we derive something new from it. And then we again derive something new from it. And then we again derive something new from it. And so the way that we're solving these sort of problems when we're checking whether something is satisfiable or unsatisfiable with automated reasoning, we're just doing this proof by contradiction in a computer. And we're deriving new and new and new things until we arrive at a contradiction, or until we find out that there is nothing more that we can derive, and then we may be able to find that model or that counterexample. So we'll be taking a closer look at two different approaches to automated reasoning. One of them is called SMT solving, and the other one is called saturation-based theorem proving. And I have worked in some extent with both of them, but I do know a bit more about the saturation-based theorem proving. But anyway, so let's start with the SMT solving. So the SMT here is just an abbreviation for satisfiability modulo theories. So satisfiability that I already mentioned, that just means that we're checking whether a formula has some model, ergo can hold, or whether it is unsatisfiable and therefore there is no way that this thing would hold. The modulo theories part, it just refers to the fact that we can be reasoning about logical formulas that are also using integers and their linear or nonlinear arithmetic, or real numbers, or arrays, or data types, or a lot of other different things. Now, the way that SMT solvers work is very modular. So they have these subcomponents for reasoning with different theories. So one component for each theory. Then there is a component that is exchanging equalities between these theories. There is a component that is focusing on the propositional structure of the formula. There is a component that is taking care of the quantifiers. And the way that SMT solvers reason for a particular formula is that they take the formula and break it into parts, such that each part is only using a single theory. And then this part can be passed on to the corresponding prover, or the corresponding subsolver for that given theory. And then when that subsolver discovers something that might be relevant for other solvers, it exchanges it using the other components, namely the component for equalities, again with other subsolvers. And so this is the high-level idea of how SMT solvers work. What is important from the user perspective is that they are in general great with reasoning with different theories, because they have these subsolvers which, when possible, employ complete decision procedures. So for some particular theories, SMT solvers are even complete. So that means that if the formula is satisfiable, the SMT solver is guaranteed to show that it really is satisfiable. If it is unsatisfiable, the SMT solver is guaranteed to show that it is unsatisfiable. SMT solvers are also good in finding models. So by models here, I mean the counterexamples or the failing test cases. And the SMT solvers that you might have already heard of are Z3, CVC5, YICT, and then there are many others. And this is actually the point where I would like to do a demo. So is the font size now large enough, or should I continue with increasing it?
This is good.
Okay, so let me just copy this. We'll be running the SMT solver Z3 on exactly the input that you've already seen on the slides. So this is our deposit example. So we can just go ahead and run Z3 on it. And it actually finishes very quickly. And it tells us that this example is satisfiable, as many of you might have expected. And it gives us a model. And this is the model. Before going into details, what the model tells us, I would like to showcase what Z3 can do on a different example. And the different example is an actual industry benchmark or an industry file that we generated at Certera when we were verifying client smart contracts. And so while the toy example formula looked like this, so it had something like 12 lines of the logical formulas. The actual industry benchmarks are much, much larger. And the formula that we generated for this particular problem is this long. It has, well, over 6,200 lines. And it contains some pretty complex operations. So this is something that would be very hard for a human just to read all of it. And definitely it's not easy to make any sense of it. Now, this is even more confusing than it would necessarily have to be, because for me to be able to use this benchmark, we had to anonymize it. So all the variables and constants and functions and everything in this benchmark is just called X and then some number. But we can see when I scroll down a bit more that there are some larger assertions here saying that, oh, well, there is something that is equal, and it is equal under the assumption that this thing holds, then this has to hold, and so on and so on. And there is some arithmetic going on and so on. So we can run Z3 also on this one. And while it runs, I will go back to our slides and I will show you what I meant by Z3 finding the model and what is it good for. So this is exactly the output that we got in console for when we called Z3 on our deposit example. It tells us that the example is in fact satisfiable, and it gave us the model. So the model, those are the values of the constants or the variables in the file for which the negated formula holds, and therefore the original formula doesn't hold. So these form the counterexample. And the model tells us that such a value of D, so value that we're depositing, is this one. And we can see it is just one smaller than the value of the 2 to the power of 256. So this is 2 to the power of 256 minus 1. And that the initial balance for which this assertion fails is 1. And we know that, yes, indeed, if we sum together 2 to the power of 256 minus 1 plus 1, then we get 2 to the power of 256. And then that modulo 2 to the power of 256 is 0, and 0 is not greater or equal to 1. So this gave us the specific point for which our property doesn't hold for the function. Okay, let's go back to, yeah, okay, this is still running. So let's keep it running for a little while more. And in the meantime, let me get to the saturation-based theorem proving, which is the second approach to automated reasoning that I wanted to mention here. It is also working.
One question. Sorry.
Sure.
Sorry.
Yeah. No, it's completely, yeah. That's why I'm here.
So the SMT solver, right? So we need to make sure that the solver itself is not dependent on, overflow problems in the solver while it is computing its results. So is that so it cannot be, for example, dependent on the limitations maybe of the hardware that it's running on, maybe a 32-bit system versus a 64-bit system or something like that. And so is this run through simulation to make sure that, so it's like a completely, is it a software solution which does not, to keep it siloed from hardware influences?
In a way, this is a like the age-old question: who will verify the verifiers, right? No, in a way, no. Okay, no, I'm running it just simply as a binary on my computer without any additional layers. And yes, it can be the case that there can be bugs in the solver itself or somewhere in the interface that will then mean that we won't be producing something that is reliable. However, if we indeed produce such a counterexample, then we can just check the counterexample whether it really holds. Because once we have the counterexample, it is usually a very simple check to see if it really is a counterexample. So this is the upside. But yeah, like, of course, there can be bugs also in the verifier and also in the solver.
Okay, got it. Thanks.
Okay, maybe we can go back to, okay. Yeah, So coming back to our more complex example, we can see that now Z3 told us that the example is unset. And that means that the original formula that the example was built from is holds, or that means that the original property really held for the program that it was trying to verify. Now I cannot tell you what the property was because the benchmark was anonymized, and actually I don't even have access to what exactly the smart contract was that it was coming from. But yeah, now we see that the solver verified that really the property held in this case. As you can see, in this case, we don't have any output that could be so easily to verify. And that is because the SMT solvers are a bit worse in producing proofs that they are in producing counterexamples or models. And that leads me back to talking about the saturation-based theorem provers, because those are the automated reasoners that are on the opposite side of the spectrum. So they are worse at producing counterexamples, but better at producing proofs. Now, the way that saturation-based theorem proving works is, again, proof by refutation. Again, we're looking for a contradiction based on the given assumptions and the negated conjecture. And to do this, we are using a so-called saturation algorithm with a set of inference rules. So first, the inference rules, or a calculus that we're using, this is just a set of rules in the format of some premises implying some conclusion. And we're using sound or correct inference rules, and that means that we know that if the premises are valid, then also the conclusion is valid, and hence it is safe to derive the conclusion given the premises. Now, in a saturation algorithm, we do it in the following way. We create a set of consisting of the assumptions and the negative conjecture called the saturation set, and then we saturate this set with new and new conclusions that we derive. So what we do is that we can essentially, this is a bit of a simplification, but essentially we can forget what were assumptions, what were conjecture. We just have some formulas in the set. And then we choose some formulas from the set and derive a new formula using an inference rule. So we choose such formulas in the set that they match premises of some inference rule, and then the inference rule tells us what is the conclusion. And that is a formula that we add to the set. And then again, we choose some other formulas in the set and again match them to premises of some inference rule. The inference rule tells us that this is the conclusion. We add that conclusion to the set. And we iterate this process over and over again until we hopefully find a formula that corresponds to falsum, so that corresponds to the contradiction. So that means that we manage to derive a contradiction by using only correct inference rules, only correct inference steps, and therefore the original set of formulas that we had was unsatisfiable, and therefore the conjecture has to follow from the assumptions. Now, when we manage to do this, we can retrace our steps going back from the contradiction, and this will give us the proof, which is then just a list of individual steps, each step only depending on formulas that we've derived before. And this is again something that can be checked in an automated way. So this gives us some additional guarantee that really what we found is correct. However, there is of course the possibility that this procedure of deriving new and new formulas either won't finish at all, or just won't finish before we reach the timeout or before we run out of memory. And in that case, we do not know whether the formula that we were trying to prove is or isn't satisfiable. There are some extensions to saturation-based algorithms that allow us to also find models if the formula is satisfiable, but they are not as advanced, and therefore saturation-based algorithms and theorem provers aren't as good in finding counterexamples, but they are good in finding proofs. And also, compared to SMT solvers, they handle quantifiers well. So if the property that we're trying to prove has a lot of quantifiers and quantifier alternation, this might be a better choice than using an SMT solver. On the other hand, if the formula that we have uses a lot of different theories, then an SMT solver would be a better choice. And then the saturation-based theorem provers that you might have already heard of are vampires of proposition E, and then there are a lot of others. And okay, since I'm already running out of time, I will go on with its main takeaways and just a quick summary of what I was talking about. So I would say the main takeaway here is that formal verification exists, and please use it if you can. It is a method that is complementary to testing. in a way, it can provide some soundness guarantees, but also in some cases, it can help with finding bugs. And yeah, that's it. So if you have any questions, I'm happy to answer them. Or otherwise, you can also reach me at my email address that you see on the slides.
Thank you. This was really great and very insightful. I definitely learned a lot of new things today about how verification actually works in practice. If there are any questions, please feel free to post them in the chat, or just unmute yourself and ask. In the meantime, I think I have one question that probably I can ask.
Mm-hmm.
So can you extend a little bit about like the details of how internally this automated reasoning works? I have only used the tools so far, but I have never learned in detail.
Yeah. So for the saturation-based theorem provers, it really is what you see here. So we are maintaining this set of formulas, and then we are looking in the set of formulas to see, oh, maybe we could apply some inference rule on this thing, and we go ahead and do it, and so on. And of course, under the hood, it is a lot of very optimized code. So for example, we aren't just keeping one set of formulas like this, but we have divided it into multiple subsets. So we know what are the formulas that were already processed. And when we are selecting formulas to apply the inference rule on, then we're only looking on pairs or triples or subsets of formulas such that there's at least one new that we haven't looked at yet. We are also keeping all these formulas and all the terms in the formulas in indices so that we can retrieve them very easily, and we can very easily check whether they really match the intended premises of the inferences, and so on. So this is under the hood how, like, there's a lot of algorithms and data structures involved in how this works. And similarly for if we go back to SMT solving, then there are different algorithms for checking satisfiability with respect to just one theory. As I mentioned, for some theories, those are decision procedures, which means that they will provide an answer. For other theories, the problem is undecidable, and therefore there's just some best effort algorithm that might be able to find the answer or also might not. So there is a lot of over approximation, for example, going on. If we're working, for example, with nonlinear integer arithmetic that is undecidable, we can over approximate it either by linear arithmetic or by using bit vectors. We can also approximate it by using nonlinear real arithmetic. So there is some delegation between different solvers going on. And again, it all depends on very efficient algorithms and data structures, because we're trying to optimize this as far as we can.
So when we are talking about, deriving the formulas and everything, so is it like all like a program synthesis based techniques working underneath the, theorem provers to derive the formulas, or like how does it work? Like usually, when we use Z3, for example, that's where we always write our own assertions, right?
Yes.
We tell everything to the solver, and then that's how we verify. We do not expect the solver to construct the correct formulas as well. But
well, in a way, actually, we do even with Z3, right? Because you pass some formulas to Z3, but then Z3 will derive new formulas from there. So if you tell Z3, for example, that A is equal to B and B is greater than 3, then it will derive that A is greater than 3 as well.
Right.
So
okay.
There is this derivation process going on. And in a way, in this saturation paradigm, there are also new formulas being derived, but only given these inference rules, which can be seen as templates.
Yeah.
And at the same time, there's always this guidance within applying these inference rules that we are sort of trying to derive smaller and smaller formulas, because we are trying to derive the contradiction in the end, which can be seen as the empty formula, because the empty formula has nothing to be satisfied. And so we have this direction of the proof that we are starting with some formulas and we're trying to derive something smaller and smaller and smaller from it until finally we find something that is empty and that corresponds to the contradiction.
Okay. And one follow-up question as well. So, while, researchers, kind of focus on, or the developers, they try to focus on designing these automated reasoning techniques, what are the design principles they keep in mind? Like, is it more about making sure that it works in a performance efficient way, or is it something different? Like, how
That
is it?
definitely as well. A major one, even probably the most important one, is that we're always trying to keep this system sound. So we'll be going actually back to the question that we had during the talk. How can we trust that the system is actually doing what it is claimed that it's doing? So yeah, so we have to make sure that whatever functionality we're adding, it has to preserve the soundness, and then it also has to be very efficient. And there is, in a way, a trade-off between these two, because what we're doing quite a lot is when we're adding a new feature, we are adding something that the prover wasn't doing before, and hence it will be doing some extra work now. But we also want to keep it efficient, so we want to keep the amount of extra work to a minimum. So we always have to be sure that actually the extra work that we're doing to achieve our goal is worth it. And yeah.
Okay. Yeah, thank you. And I think, yeah, we can stop recording as we are, transitioning into the AMA right now. And to the audience, please feel free to ask questions. I'm just going to stop the recording for now.
Thanks.